Let me start with the question that puzzles everyone. Why are we trying to quantize gravity when we can never probe it experimentally?
So the main reason that various people, as you know, from people like Dirac and Feynman, and for several decades, have been trying to do it. And the reason is because we currently have two rather diverse uh, views of how to describe nature. One view, of course, comes from quantum mechanics, and it has a conceptual structure and conceptual framework, and that is supposed to be applicable to everything. It's not that just for electrons we've got a Hilbert space and operators. No, the quantum mechanics is a conceptual framework that says that no, given any physical system, it is to be described in the following way: with Hilbert space, operators, eigenvalues, eigenfunctions, then physical meanings, and what you measure in experiments, and so on. And the mathematics that it uses is really basically functional analysis, Hilbert spaces and operators and so on. The general relativity, on the other hand, surprisingly makes a very similar claim. It says that given any physical system, it is to be described by some fields, that tensor fields, scalar fields, vector fields on the manifold, which is a smooth manifold. These fields are smooth; they satisfy hyperbolic differential equations. So the propagation is in a light cone; it's all causal, and so on and so forth. And so these are two very different claims that are made. General relativity uses this pristine, geometric, precise, deterministic predictions. Quantum mechanics is algebraic and functional analysis, and the predictions are fundamentally probabilistic. The mathematical structures are different, conceptual structures are different. So in a certain sense, we live in a kind of a split brain world when we do physics, and that cannot be. And that the point is that there has to be a unified way of looking at nature, and these two things that we come across are going to be special cases. And this is very similar to what happened with Einstein. One can ask, in fact, Max Planck did ask Einstein, why are you working on general relativity? First of all, if you change Newton's theory, you won't succeed. And if you succeeded, no one will believe you. I mean, even Planck said that way. And Einstein persisted because, again, for this idea that you cannot have one description of nature in which there is absolute simultaneity, as in Newtonian gravity, and another description of nature where you have got Lorentz invariance and no. And so there has to be a grander theory from which these emerge. And we are looking for the same thing. And I disagree with the last part of the question that it will never be observed. And after all, when Einstein did this theory, one did observe it. But the real genuine observations of general relativity came like with gravitational waves and black holes, it came a century later. And that is just because technology was not up to the mark in order to detect those effects. We don't doubt that space-time is curved even around us, but we needed black holes to see the actual manifestation. And so similarly here, it will going to take time, but perhaps we can also discuss about where we are with respect to observational prediction later.
One of the candidates for a correct theory of quantum gravity is loop quantum gravity. Could you please describe this?
The idea of loop quantum gravity is really to take central lessons of general relativity that Einstein taught us very seriously, and to sort of say elevate them to a quantum mechanical level. So that we have a genuine unification of general relativity and quantum physics. So I don't generally like the word quantize, although it is used as a short form. It really is a unification of two different theories. So the idea about of the basic ideas of loop quantum gravity then are the following: that Einstein taught us that space-time geometry is a physical entity, exactly like matter. You can act on it; it acts back. Now, matter has atomic constituents. Things look smooth. The screen that we both are looking at, looks very smooth to us, is very well described by continuum. But we know that if I went and zeroed in with an electron microscope, I will see that it has atomic structure. And this is, so in loop quantum gravity, the idea is that space-time geometry is a physical entity. It is not a spectator. It acts, it reacts, and therefore it should also have an atomic structure. And how do you describe this atomic structure? Well, the smooth continuum of space-time is described by Riemannian geometry in general relativity. So here, in loop quantum gravity, one goes and says that one needs a generalization of Riemannian geometry, and that is going to be quantum Riemannian geometry. Again, gravity is encoded in geometry. Gravity is quantum mechanical in nature. Therefore, geometry should be quantum mechanical in nature at a fundamental level. It should have atomic structure. It should be described by, there should be operators corresponding to physical observables, like areas of the screen that you are seeing should be quantized, and so on and so forth. And so the idea here is that space-time fabric, if you like, looks like a continuum, but it's a fabric woven by quantum threads. And the question is how to bring out the nature of these quantum threads. And that is what loop quantum gravity people did in the 90s when they developed quantum Riemannian geometry.
Physicists are divided among themselves as proponents of string theory or loop quantum gravity. What do you think are the fundamental differences between the two?
I think that this kind of division is artificial. I mean, these are two different paths, and to say that one is the true way and the other is wrong, it doesn't make any sense to me. I mean, to me, they are complementary. They emphasize different things. Both of them may be correct. The final theory may actually have elements of both, or neither of them may be correct. And there's a complete third thing available. But I think that this division is not really, it's not as though there is one is right and the other is wrong. Okay, so what are the differences? That they differ from each other in almost most essential ways. So loop quantum gravity, as I mentioned, arose from general relativity, and therefore geometry, space-time geometry, and the atomic structure, atomic nature of space-time geometry is at forefront. Non-perturbative methods of general relativity at forefront. And so the viewpoint is that, well, yes, quantum field theory has been very successful and in other interactions, but in other interactions, we could treat space-time as just a background, and which is kinematical, which had no physical degrees of freedom of its own, etc. And therefore, the framework that is used in quantum field theory, therefore, is not appropriate as it stands for loop quantum for quantum gravity, and we really need this Riemannian geometry in terms of which we will formulate all of physics. And this is what I was saying before, that this unification will give you a new language, a new syntax, new framework in which to form physics. String theory comes from the fundamental from quantum field theory community, and they take quantum field theory as being fundamental. Even in non-perturbative formulations such as ADF, CFT, we still work with fundamental theory. It's still quantum field theory. Just it's on a boundary, but still a quantum field theory with all the standard ideas of quantum field theory. So this is kind of a difference. Another difference is what one is, where one is going to be conservative and where one is going to be radical. In loop quantum gravity, one feels that, well, things which had not been observed in nature, in spite of the fact that repeated experiments have been made, should not be at the fundamental and the foundation of the new theory, such as supersymmetry, higher dimensions, negative cosmological constant. So they should not be at the foundation of the theory. In string theory, on the other hand, one wants to say that unification of all interactions should be fundamental. This goal has not been reached, but that was the starting point of string theory. And in string theory, ideas from quantum field theory, standard quantum field theory, in ADS-CFT is even been classical quantum field theory because of the boundary, that or conformal field theories, those are to be regarded as fundamental. So what is radical, what is conservative? the sense of values is very different. They arise in different ways. And I think that is very healthy. We need a variety, as Feynman used to say always. We need a variety.
Einstein's theory of general relativity completely changed the way we perceive space-time. How does loop quantum gravity reshape our intuitive understanding of space-time?
As I mentioned before, in general relativity, space-time, as you said, is different from what it was in Newtonian or even in special relativity. It's a physical entity described by geometric fields and so on. But there is still a smooth continuum. And whereas in loop quantum gravity, the idea is that space-time has specific atomic structure. These atoms of space-time, these elementary excitations of space-time, are what we often call atomic structure, right? Because in Maxwell theory, for example, we say we got photons, and that is atomic structure of a classical continuous electromagnetic field. So what are the fundamental excitations of the theory? That is what we would like to say. And according to loop quantum gravity, these fundamental excitations are not, so to say, one-dimensional, are not zero-dimensional, they're not point-like, but they are really one-dimensional. So in this respect, actually, it is not so different from string theory at least when it began. So the fundamental excitations are one-dimensional, and these are polymer-like, and they are really woven tightly together in everyday situations. And the analogy that I've given a million times is, that of the fabric of your shirt. You look at the fabric of your shirt and look like a completely smooth, continuum. But you just have to take a magnifying glass to see that it is woven by one-dimensional threads. So this two-dimensional nature is an illusion of coarse graining. If I just take a magnifying glass, I see that there are one-dimensional threads which are crisscrossing. And the same thing is true, therefore, in loop quantum gravity. So that is where we differ. It is not a smooth continuum at a fundamental level. It has a very specific polymer-like structure, but when coarse grained, continuum emerges. And then this coarse graining approximation is very, very good in normal circumstances around us. But when you go to extreme regimes, such as the Big Bang or inside the black hole, where the curvature reaches Planck scale, then this smooth approximation would break down and it has to be replaced by something else. In other words, that is where the quantum threads come into their own. The fabric of space-time is violently torn apart, and we have to deal with fundamental building blocks. Just to give an analogy, if I got water, I can use hydrodynamics, continuous picture or something. But once I boil it, there's sufficient energy scale, then I have vapor, and the vapor is something that you deal with individual molecules. So you can do statistical mechanics with molecules. So similarly here, the statement is that we have to deal with vapor, if you like, at this near the singularities. We have to deal with these fundamental building blocks, like molecules in the vapor. We have to deal with fundamental building blocks of the space-time fabric. So it does take us beyond Einstein's general notion of space and time, as you said.
So earlier you talked about quantum Riemannian geometry. What does it even mean for a geometry to be quantum?
So this is again a blending of the syntax to create new syntax. The syntax we got for quantum theory is Hilbert spaces operators. Syntax we got from general relativity is kind of continuum and smooth pictures and such things. So in general relativity, for example, if I look at the area of the screen that we're looking at, it can change continuously. Right? And the reason is because it is described, there's a formula in Riemannian geometry which will tell you square root of intrinsic metric h, square root of the determinant of that, d2x, and any coordinate system, you calculate it and you'll find it is continuous. I can change it continuously. On the other hand, in loop quantum gravity, by quantum geometry, we mean that the geometrical observables, such as the area of the screen, the volume of this room, a length of curves, these are not functions of of a smooth metric given on a continuum, but rather they are operators on a Hilbert space. And then these operators, as you know, in Hilbert space, often have discrete eigenvalues. And so it is really true that detailed calculations have shown that the area has only discrete eigenvalues. Volume has discrete eigenvalues. So that means that in the usual parlance, area is quantized, because for a hydrogen atom or a simple harmonic oscillator, when energy takes discrete eigenvalues, we say energy is quantized. So in this sense, this area or volume are quantized in general relativity. So that at a fundamental level, the picture is very different from that of classical general relativity. So the notion that there is a quantum Riemannian geometry means we have notions, observables, which come from Riemannian geometry, but they are now described using Hilbert spaces and operators.
So, as you discussed earlier, changing the very notions of space time and geometry can lead to fundamental changes in our understanding of gravitational objects like black holes and the initial singularity of the universe. How do these objects get modified in loop quantum gravity?
I think maybe I should begin with the singularities. Both the Big Bang initial singularity as well as the final black hole singularities. These are places where general relativity fails. In other words, you use general relativity to calculate until you reach a singularity, and then everything goes up. As Veera used to say, there is a smoke, and general relativity refuses to answer. Physics breaks down. But as we have seen again and again, for example, even the elementary theory of atoms, classical theory, the electron should be radiating and should form the nucleus in no time, so the atom could not be stable, and so on. And then there is a singularity at the origin of the potential, because the potential is infinite. But anytime this happens, where theory just predicts infinities for physical questions, it has been a signal that you are pushing the theory beyond its domain of application. And therefore, when you take a better theory, then these problems will be alleviated or completely removed. So what happens in general relativity, in the simple language, is that you've got a space-time continuum, a fabric of space-time, a space-time continuum. And then the fabric, this picture just ceases to be meaningful at the singularities. Loop quantum gravity then says, yes, that is because that was a coarse-grained approximation. You have to go to the fundamental building blocks. And therefore, you have to use these equations that come from loop quantum gravity, in which, for example, there is a minimum non-zero area. Area is not a fundamental concept. And this thing called area gap plays a very fundamental role in corrections to Einstein's equations. And for those because presumably your audience is physicists, so then the statement is that normally curvature, in classical theory, you can describe it by either just a locally tensor field, or you can describe it by saying that, well, I take a holonomy around a closed loop, divide by the area, and -1, and then take the limit, and that gives me the curvature. And this is what we do, for example, for Maxwell theory. I can take the holonomy, the A dot dl -1 divided by the area, take the limit, and that will give me the magnetic field. So the idea here is very similar, that in fact, this area gap is very important because you don't shrink the loop all the way to zero, but to the minimum area. And that produces a fundamental non-locality, if you like, but only at the Planck scale, because the minimum area is Planck length, is Planck area. And so in loop quantum gravity, when you do this, Einstein's equations are modified, and the leading order connections to Einstein's equation resolve the Big Bang singularity and also the black hole singularity. So this is what happens in the singularities. So at the horizon, the idea is that one writes down some conditions in classical theory which hold at the black hole horizon. And then one elevates them to the quantum level as operator equations on permissible states. So when that equation is satisfied, that is when there is a quantum horizon. So it's called the quantum horizon condition. And the picture that emerges is the following: that horizon is topologically two sphere, two-dimensional manifold. But the reason why it has any area is because, actually any surface has an area, is because there are fundamental excitations of geometry and then they intersect. For example, we've got the screen, and there are fundamental excitations of the geometry which actually come and intersect the screen. So here is the screen, and the fundamental areas are the excitations, and each excitation can deposit a quantum of area. It could be the Planck area, it could be 12. It's basically square root of j into j plus 1, where j is an integer, times. So those are the eigenvalues. So you get quanta of area. But there are so many fundamental excitations that when you add them, all these little deposits, and they give you the macroscopic area. The picture of the black hole horizon then is that really the horizon classically is a smooth surface, but quantum mechanically, the area, its origin is these intersections of the fundamental excitation of geometry with this particular surface. And certain equations have to hold at the intersection. This is the quantum horizon condition for that surface to have the interpretation of area. So that is the picture of the horizon. And then the entropy and so on is coming because one is doing a coarse graining and statistical mechanics of these punctures. And from that, the notion of macroscopic notions such as entropy arises.
Describing gravity through this new lens of loop quantum gravity also leads to the field of loop quantum cosmology. What is this new field and what does it predict to be the fate of our universe?
Loop quantum cosmology is really application of methods of loop quantum gravity to symmetry reduced models. Our universe at a large scale is homogeneous and isotropic. So if you're only interested in those degrees of freedom, and we coarse grain over other degrees like anisotropies, homogeneities, there may be other local like fluctuations. We really coarse grain over them. Then what is left can be described with a system with only finite number of degrees of freedom. And then we can take this system, which is basically cosmologies, and we take this system and we apply to them techniques from loop quantum gravity. And the fundamental nature of quantum geometry, with discreteness and so on of area spectrum, that still descends in this particular case. And so, for example, quantum Einstein's equations are again modified because curvature is denoted by an operator in which you take a holonomy and you shrink the loop only until it reaches the minimum area. And so that gives quantum corrections. And when these quantum corrections are included, to me, it was a huge surprise that automatically the Big Bang singularity is completely resolved. So there is nothing else put in by hand. It is not like the Hawking new boundary condition. There is no negative energy matter. All the matter fields satisfy positive energy conditions up here. But Einstein equations themselves are corrected. These corrections, amazingly, are totally negligible when the energy densities and curvature is about 10 to the minus 3, 10 to the minus 4 of the Planck density, Planck curvature. But once it approaches the Planck area, these corrections grow enormously. They produce a repulsive gravitational force, brand new nature. And that actually causes the sort of halts the Big Bang and causes a Big Bang bounce. And therefore, the Big Bang is replaced by a big bounce. And this is really because of quantum geometry effects, not because there's some negative matter, there's anything else. And again, to me, it was amazing. I initially didn't believe it. We kept the paper for 6 to 8 months in order to just check and recheck that there are no hidden assumptions or special things that are special initial conditions that were used and so on, the calculations. That the surprising result is that, again, on the other side of the Big Bang, then, when the curvature falls to about 1,000th of Planck curvature or 10,000th of Planck curvature, then again, classical general relativity becomes a good approximation. So you have got a pre-Big Bang branch, which is collapsing. And then there's a quantum bridge in between. And then there's a current expanding branch. So the pre-Big Bang branch is contracting, quantum bridge, and then expanding branch. And in between, the singularity is replaced by the big bounce.
What unique signals in experiments would help us confirm the theory of loop quantum gravity? Can the Webb telescope help us?
You all know, we can never prove a theory. We can only disprove a theory. So, for example, gravitational waves don't prove general relativity is correct, but there has been no tension with general relativity. And When a theory starts working in many cases, like quantum electrodynamics, for example, then we take that theory seriously until it breaks down. And then, of course, all these theories are blemishes of their own. Singularity to general relativity, infinity to quantum field theory. And so then we say that, well, in that regime, we need a new description up here. Okay, so the signatures are going to come, in fact, there are already some signatures. They're going to come from the resolution of the Big Bang singularity. Since we have limited time, let me just take the leading paradigm in cosmology these days, which is the inflationary paradigm. So the idea is that one starts with at the onset of inflation, when the universe is assumed to be homogeneous and isotropic, except for the quantum fluctuations of the cosmological perturbations. So cosmological perturbations, both matter and gravitational perturbations, they are treated quantum mechanically. And this is a big difference in the last 3 decades versus what was done before, that the new generation may not be aware of. Previously, when people were talking about the early universe, they were still using classical general relativity. Now one is using classical metric, but perturbations, one is treating quantum mechanically. And these perturbations have irreducible Heisenberg uncertainties. They cannot be zero. I mean, there will always be some fluctuations, and that is what one is focusing on. And the one is assuming that these fluctuations are in the so-called Bunch-Davies vacuum at the onset of inflation. Inflationary phase is approximately de Sitter, and in de Sitter spacetime, because of symmetries, you can single out a vacuum state, and therefore one says that the onset of inflation, the state was the Bunch-Davies vacuum. I mean, it is not exactly de Sitter, and therefore there is ambiguity, but for observational purposes, this ambiguity does not make any difference. You can change when it was de Sitter slightly, and then it doesn't make any difference. But this all happens kind of there's a Big Bang, and then as time goes on, there's a later time, and the onset of inflation is a little bit later there. So the initial condition is put a little bit later, right? It's at the middle of evolution, so to say. Why can't I go back all the way to the Big Bang? Well, because one is using classical general relativity, everything is infinite there. I cannot put the initial conditions there. So this is a little bit of an artificial nature of what one is doing in the Big Bang. And so what we can do is really put the initial conditions at or even to the past or the big bounce, and then we evolve. Then by the time you come to the onset of inflation, your state may not be a Bunch-Davies vacuum. There may be some small fluctuations. Now, again, 20 years ago, the standard response from the inflationary community used to be that, yeah, there are fluctuations, but inflation will just wash them out. Inflation is amazing. I mean, basically, hydrogen, something of the size of an hydrogen atom, gets expanded during the 65 E-folds to the size of a Milky Way. Right? So this is a huge expansion. So if you have little fluctuations, they will be just diluted away. But what happens is, when you do quantum field theory in curved space-time, and space-time geometry itself is highly dynamical, what happens is that there is also spontaneous, in addition to the spontaneous emission, there is also stimulated emission. And so as it is expanding, more and more excitations are created. And it turns out that the number density of excitations remains the same during inflation, no matter. So it's not diluted because of the spontaneous, because of the stimulated emission up here. It's not diluted, it remains the same. And therefore, at the onset of inflation, the state is not exactly the Bunch-Davies vacuum. It has some departures from it. And very interestingly, these departures have observational signatures. These signatures are, again, subtle and surprising, are at the longest wavelength, so at the largest angular scales. And what one finds is that at small angular scale, there is excellent agreement with inflation, but at the largest angular scale, there are corrections. Now, in standard CMB observations, they work very, very well at the small angular scale, at small wavelengths, large K, large wave number. But at the largest angular scales, basically the violin decomposition, the L mode less than 30, there are some anomalies. The significance of any one of these anomalies is small. Basically, if you were to do realizations of the probability distribution given by the theory, then in 1 in 1,000 of those realizations would have this anomalous feature, and one doesn't take it too seriously. But if you have 2 or more anomalies, then it becomes 1 in a million, 1 in a billion, and then it takes seriously. And even the Planck team in their second as well as the last third announcement of results has emphasized that there are these anomalies, and the significance of multiple anomalies is not, statistical significance is not negligible at all, and therefore they in fact implored us to look for fundamental explanation for this in primordial physics, the early universe physics. And loop quantum gravity provides such an explanation. There has been very nice work, particularly both by my group, but I think much nicer work by Ivan Aguirre's group, which actually shows that all these anomalies that one sees in CMB are alleviated, that they are brought so that our universe is actually is realized in 1 in 1,000 and not in 1 in a billion, 1 in a million. And so this alleviation of anomalies is a signature. There's a prediction also in our work. There's a prediction that you got a 6-parameter standard cosmological model, and then observations measure these 6 parameters. The optical depth is one of those parameters, and that parameter is the least well measured. It's still quite well measured, but it's the least well measured of all others. And its value also has drifted quite a lot between W map at Planck and between Kobe and W map. So it has drifted all along. So now the statement is that the prediction of our model of loop quantum cosmology, because there are also assumptions in the model to make actual physical predictions. You have to make some certain assumptions, not huge number, but you still have to make assumptions. So our model predicts that the value of the optical depth is about 10% higher than that predicted by ordinary inflation. So this is something that will be tested experimentally by different observations. The reionization depth that James Webb would actually be able to measure. The question is how accurately and details of it, but that could actually give you the optical depth. And so, if you like, so this can be falsified. This particular loop quantum cosmology model can be falsified, but it could also be verified. If it is verified, then people would take it much more seriously that in fact there was a prediction, not a prediction, but a prediction. So there are predictions already. So this goes back to the first question you asked about, why do quantum gravity? I always felt that, well, first of all, we have to get the conceptual framework right. But for too long, quantum gravity has remained in this perch of conceptual and mathematical issues and not making contact with observations. But the early universe has provided loop quantum gravity an opportunity to make contact with observations, and we are using it very actively.
Adding to the previous question, what are the future directions of loop quantum gravity, and what can physicists working on loop quantum gravity expect in the next 25 years?
Well, very eminent physicists have been shown to have made rather silly statements when they were asked for predictions. It is Lucasian inaugural lecture of Steve in Cambridge, Stephen Hawking. The title was "Is the End of Physics in Sight?" And he really said that, well, now maybe very soon any coordinate supergravity would be the final answer, and then we will be just reduced to engineering and so on. I can go on. All the eminent people have made so I don't want to venture into saying, well, what will happen or what will not happen on such a grand scale. But what I can say is there are opportunities, and there are 2 kinds of opportunities. The first opportunity is more observational, and here I really think that it is going to be the early universe. That is the best laboratory, and not even gravitational waves and black holes. Those effects will be very difficult that those effects can be detected in the next 25. The quantum corrections to those to the observations of gravitational waves would be useful in the next 25 years. In other words, observations will not be accurate enough to to actually be able to measure this quantum gravity correctly. In the early universe, I think that, for example, optical depth, Bohr and such things will actually happen. The second frontier is more conceptual. This frontier has to do with uh, particularly new development that is really taking off in quantum gravity. I'm only marginally involved in it, but I am involved a little bit. But other younger people are driving it, and it has to do with the interface between loop quantum gravity and quantum information. And I expect that that field is going to sort of really grow very much in the next 10 years or so, because there is a lot of interest from the quantum information side also on this. And this is a very fascinating field because, you know, first of all, when ideas come from two different fields, it's very fertile, but you can also see that each field is naive with respect to the concepts of other ones. I find quantum information to be very valuable, but their ideas are so implicitly, their intuition is so tight to non-relativistic quantum mechanics that, you know, they don't understand or fully understand, they don't fully take into account the subtleties of quantum field theory and the basic issues. They use the same words, but they mean quite different things in quantum field theory and in quantum information. And so I think that there is a big kind of activity, big interaction, big debates, and these are going to play a big role. And then there will be other conceptual issues, particularly like the issue of information loss. I do think that that issue will be resolved within the quantum gravity also in the next 25 years. So there's a specific thing that will be resolved. I don't want to make a grand prediction. I do not think that loop quantum gravity is, as it stands, even when it is completed, as it stands in its current program, that it will be the final theory. It does not take into account, you know, all of physics. It emphasizes the effect of quantum nature of gravity on the rest of physics. And that is why it is of interest to quantum information in particular. But it does not take into account, you know, the unification of particle physics with gravity. On the other hand, you know, even today we do not have grand unified theory, even if you forget about gravity. So that's a long road ahead. So loop quantum gravity is going to shed more and more light on the implications of quantum nature of gravity on rest of physics, and not on. I mean, in this respect, this is different from what string theory is doing, because, you know, lately there have been articles, for example, even in the website of Institute of Advanced Study, the journalist in residence, her name was Cole, and she wrote an article which is on that in the website, which says that string theory has now kind of, they say, second rebirth of string theory, and they say string theory has not lived up to its promise of unifying general relativity with gravity, general relativity with quantum physics. On the other hand, it has had a rebirth of a very rich set of tools which could be used all across physics. And I personally, I feel I agree with that sentiment. Whereas what loop quantum gravity is doing is really exploring this quantum nature of gravity and how quantum nature of gravity could be seen in other interactions. It is not providing such a rich set of tools to the rest of physics as the string theory is providing. So this is a sort of a difference between the future of the two things. Rich set of tools which could be used, adapted, and so on and so forth. But that is not shedding any direct light on quantum nature of gravity, whereas in loop quantum gravity, no such. We don't have tools of such a great power, comparable power. On the other hand, what is exploring really the effect of quantum nature of gravity. So this is a contrast between the two for the coming years.
Thank you for this amazing session. Lastly, what piece of advice would you like to give to a young audience?
Young people, particularly, say graduate students. Let me start with graduate students, I can go back. With graduate students and so on, I think that what tends to be too absorbed in one's thesis problems or in the area in which one thesis is, I really strongly advise that people go to departmental colloquia, for example, and try to learn what is happening, advances that are taking place outside your area, because you can make connections. I also advise to take courses. For example, when I was a graduate student, I sat in an algebraic quantum field theory course, which was actually, it was pure algebra course, actually, modern algebra, but in which I learned things like Gelfand-Naimark serial construction, which is a construction to produce Hilbert spaces starting with algebras or operators. So basically representation. And this has turned out to be extremely useful for me because we got new quantum mechanics, for example, in quantum cosmology. And that new quantum mechanics is coming because one is finding new representations of the algebra which violate one of the assumptions of von Neumann theorem. And therefore you get really completely new physics. So this breadth is important and I cannot emphasize it more. However, I should also say that as my own PhD advisor, Prof. Garosh, used to say, your interest should be like a Gaussian. It should not be uniformly spread out because then you don't make progress, you will not get a job and such things. But it should be Gaussian. So that is, it should be, that there should be a lot of depth and a lot of understanding in the immediate areas, but we should also have understanding of a lot of other areas. Less and less as you go away and away, but still those can come. Because as you grow into faculty positions and so on, you have less opportunity to learn completely different things. And so what you learn early on can be extremely useful. For even younger audience, I would say that really read, for my generation, it was reading semi-popular books, but maybe here it is more like looking at the online articles and online videos. The problem is that there are way too many of them, and many of them are complete junk. And so the problem there is distinguishing what to read, what to look at, and what to trust and what not to trust. So perhaps they can get advice from some reliable professors or something like that. But I think this general understanding the general culture is very, very important. And finally, for graduate students, postdocs, and even young faculty members, I think it's really important to realize that what you think has been obvious today may be completely superseded in 30 years from now. What was taught to me about how the elements are created in the supernova explosions, about how to deal with the early universe in terms of classical perturbations and so on, that the early universe was chaotic and it was really very, could not be described as perturbation theory, etc. No. And it is all classical. Nobody looks at it that way anymore. Everything is in terms of quantum field theory, it's all perturbative. That was the first order fluctuations, maybe second order, but you're really first order fluctuations. So the worldview can change enormously in 30 years. And, one's career is more than 30 years typically. So it can change enormously. So on the one hand, you should believe strongly and in your own work, whatever you're doing, your basic assumptions. Otherwise, you'll never make progress. But when the work is completed, then you should be your own critic, and perhaps the worst critic, and really examine it and say, well, what are the assumptions, what are the flaws, etc. Not so otherwise you can build up structures on a swampland, on a total swamp, and then it can all sink. So to be extremely critical of one's own work after it is completed is very important. And at least I think that is a hard part of research life on a long range, namely being fully enthusiastic and believing in it and putting all your energy and heart into it when you're doing it, and then detaching yourself and taking an objective view afterwards. There are many people who are very, very knowledgeable, extremely broad knowledge. They don't. I mean, when I was a graduate student, I said, well, if he can't solve quantum gravity, nobody can, because he knows everything. But that was a problem because they know everything, so they see difficulties right away. They don't do the first step. But then there are many others who are many more actually who are in the second step. Maybe they believe what they're doing and they completely ignore all the flaws of their own work. So this balance, I think, is a critical thing. So that is the strongest thing that I would suggest. It is emotionally very hard, but I think that is what is needed. A certain discipline of like that is really needed to have a sustained long-range impact. I mean, at your age, if you want to do this, right? I mean, everybody has choices. But if you want to really do physics, I mean, it should be in your blood. I mean, you should go to bed thinking about the problem. You should get up in the morning in the shower while you're taking a shower. You still are thinking about it, and then you take a walk, think about it. I mean, you concentrate, and don't look at social media or anything like that. So there has to be this this burning passion for it, I think then there will be success. That's the thing.